Hello class, this is my report from Laboratory 1, Constant Velocity Motion. Well, from Newton's second law, we have that our final velocity is defined by this expression. Our final position is defined by this one, where v sub I is our initial velocity, F net is the net force acting or of object of observation, m is the mass of that object, and delta t is the change in time, and of course r sub I is our initial position. Well, for this second law of Newton, we have that for velocity to be a constant represented by this expression, we need that all the forces that act on an object cancel each other, or that there are no forces acting on an object. All these two cases can be defined by this expression, where our net force is equal to 0. I used a little toy to make my experiment. Let's see the video on tracker. I obtained my data, time, this position versus position, and then for my model, for my computational model, I used this code. Or for my initial conditions, I used the initial position in the origin and the initial velocity that I determined with the first two measurements of time and position in tracker, all starting at time equal to 0 seconds. The observation dured almost 1 second, here 0.9 seconds. The important factor F net equal to 0 is introduced here. Here we have the expression for the velocity that we saw in Newton's second law, and the expression for the position. So when we run this model, we obtain this. When we graph the experimental data versus the model position, we obtain this. As you can see, the model position, we define it by the red line, predicts well the experimental position defined by the blue dots until almost 0.4 seconds. Then the object of observation decelerates. This can be explained by the friction with the ground and with the air. And that's all. Thanks for watching.